Hey guys, welcome back to my channel Simply Nimi. So now we are going to begin with practical series for biochemistry, that is reactions of carbohydrates will be first. Under reactions of carbohydrates you should write physical properties. If you ever get this experiment in exam for your final practicals, you'll have to write physical properties first, then chemical properties. So under physical properties you have to write appearance, color, odor, reaction to litmus. This is going to be same for all the carbohydrates, that is clear, colorless, odorless, neutral. So under chemical properties, first we begin with Molish test. So what is Molish test? In this you take 2 ml of carbohydrate solution in a clean and dry test tube, add 2 to 3 drops of Molish reagent, mix it, incline the test tube and add carefully through the sides of the test tube 2 ml of concentrated sulfuric acid. If this is positive, you get a reddish violet colored ring at the junction of the two liquids. It's very important to write these certain colors or this junction of the two liquids when you're writing it on your paper. Inference, the solution is a carbohydrate. This proves that the solution is a carbohydrate. Now, what are the precautions? We shouldn't add excess alpha naphthol, and then in presence of excess alpha naphthol, you can see the what reddish violet ring is, that right? It becomes green. This shouldn't happen. Impurities also can cause this green ring. Since water acid interaction produces heat and it can cause charring of carbohydrates, it forms a black ring. So therefore acid should be layered very slowly and carefully to minimize this interaction. That's why, right, you put it through the sides of the test tube and not just like push, you just fully put it off in it. Principle of the test. Why is this principle important? Because principle can be asked for viva, and since this is the first test which you do, examiner just skims through your paper, sees this first thing, yeah, tell me the principle of Molish test, and that's how you'll have to tell the principle of Molish test. It's very simple. Every carbohydrate shows this test. Carbohydrates, when treated with concentrated sulfuric acid, undergo dehydration to give furfural derivatives. The key word being dehydration to give furfural derivatives. These furfural derivatives condense with phenolic compounds like alpha naphthol to give a violet color complex. All carbohydrates that have at least 5 carbons answer Molish test. So composition of the reagent. Molish reagent should have something, right? That will be 1% alpha naphthol in ethanol. This can again be asked for a viva question. Next we come to iodine test. Iodine test is negative for all of the carbohydrates except starch. Only starch will give positive iodine test. But then you will have to do it just for the sake of it for all the carbohydrates. Iodine test, you take 2 ml of carbohydrate and then add 2 to 3 drops of iodine. Don't add much, just add 2 to 3 drops of iodine solution and mix well. If blue color is obtained, it indicates the presence of starch, and then if no color is obtained, it is not a polysaccharide. You just have to say that solution is not a polysaccharide, and then accept the color of iodine. That is, yellow color of iodine is still there, but it doesn't become blue. That's why you say that it is not a polysaccharide. In case it becomes blue, you say it is a polysaccharide, that is starch. So principle of the test. Iodine forms a coordinate complex between the helically coiled polysaccharide chain, and iodine is centrally located within this helix. Why is this? It is due to adsorption. 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 It's not absorption, it is adsorption. And then iodine color obtained with the polysaccharide depends on the length of the unbranched linear, that is alpha 4 linkage chain available for complex formation. And then starch gives a blue color with iodine. That's what we have written there, right, in observation and inference. And composition of the reagent, it is 1% iodine and 10% potassium iodide. Next comes Benedict's test. This is a very important test which you will be doing in first BDS again. So you take 5 ml of Benedict's reagent. They give a mini measuring cylinder. It's so cute actually. In that you take it and then you heat. Take 5 ml, put it in test tube, then again you heat. This is very important. You can't just skip this line where you just heat it where there is no color change, which is proving that there is no auto reduction. If you don't try this, you will be rebuked. So you have to write this, then you'll have to write that add 8 drops of carbohydrate solution and continue boiling for 2 minutes, allow to cool spontaneously. So you get a various color precipitate. In case of carbohydrates, you will get brick red color precipitate, and then which proves that the given sugar is a reducing sugar. If there is no colored precipitate, it says that it is a non-reducing sugar. So based on the color, you can see the amount of sugar present in it, but in carbohydrates it's going to be brick red, which will say that this sugar is a reducing sugar and not a reducing sugar if it is no colored precipitate. So there are certain questions they are asking Benedict's test. Why is this a semi-quantitative test? This is because the specificity, that is fixed volume of reagent, fixed volume of sugar, that is 8 drops, which is 0.4 ml, is put, and then when this test is conducted, it gives a rough idea of the sugar content. That's what 0.4 ml, 8 drops, is giving a brick red. So you can just estimate the kind of sugar content in the test solution. Based on the color of the precipitate, the approximate concentration of glucose is known. 1 plus, 2 plus, and so on. Basically the color, you'll know this much sugar, this color, this much sugar. Therefore, it is semi-quantitative. This is a very important Viva question. They ask, why is Benedict's test a semi-quantitative test? Then Benedict's test is frequently used for detection of sugar in the urine of diabetic patients. Coming to principle of Benedict's test, this is specific test for reducing sugars. Reducing sugars under alkaline condition tautomerize and form NADiols, which are powerful reducing agents. So these can reduce cupric ions to cuprous ions. Copper sulfate is reduced to a red precipitate, which will become cuprous oxide. Now composition of the test, what and all it's going to be there. Copper sulfate, which gives cupric ions. Sodium carbonate, which makes the medium alkaline. Sodium citrate, this is a important question. Sodium citrate is a stabilizing agent. It keeps the cupric ions in solution. It prevents the precipitation of cupric ions as cupric hydroxide by forming a loosely bound cupric sodium citrate complex, which on dissociation gives a continuous supply of cupric ions. So the sodium citrate, it acts as a stabilizing agent, which will not let the cupric ions escape by forming a precipitate. It just keeps it in the medium. Go to Barfoot's test. Under Barfoot's test, you take 2 ml of carbohydrate solution, add 2 ml of Barfoot's reagent, boil for 1 minute, cool under tap water. This you can boil for a time a bit more also, because you can't get it in 1 minute sometimes if there are impurities or if it's contaminated and all of that. You will get a scanty red precipitate which will float and it will stick to the sides of the test tube. If this happens, it says that there is monosaccharides in this. If there is no scanty red precipitate, it indicates the presence of disaccharides. So this differentiate between monosaccharides and reducing disaccharides. There are certain disaccharides which will reduce it, which are reducing sugars also, so that you can now say that which is monosaccharide, which is reducing disaccharide. Principle of the test, this test is also based on the reducing property of the sugar, but that in Benedict's test it is done in mild alkaline condition, right? But in this Barfoot's test it is done under mild acidic condition. Benedict's is alkaline and then Barfoot's is acidic condition. So cupric acetate is reduced to a red precipitate of cuprous acetate. Acidic medium is not optimal for reduction, but monosaccharides, being very powerful reducing substances, bring about a slight reduction and produce a scanty red precipitate. So basically acidic medium is not good for reduction, but monosaccharides, these monosaccharides, right, they are very powerful reducing substances. So these bring about a slight reduction and produce a scanty red precipitate. A composition of the reagent, there is cupric acetate, this gives that cupric ions which is needed, glacial acetic acid which gives the acidic medium. Next, Selvanov test. In this 2 ml of Selvanov's reagent is taken. To this 4 to 5 drops of carbohydrate solution is put, and then you just mix and then heat it for 30 seconds. Don't heat it a lot. If cherry red color is obtained, then solution is a ketose. If there is no cherry red color, then it is an aldose. Basically this glucose and fructose it is used. Principle of the test. Carbohydrates containing free keto group react with hydrochloric acid to form hydroxyl methyl furfuryl, which condenses with resorcinol to form a cherry red complex. This is that cherry red color that you get. This test is answered by keto sugars like fructose. Basically fructose gives this cherry red color. Selvanov's test distinguishes between aldoses and ketoses. It is positive for keto sugars. And then principle is similar to Molish test, in which sugars on reacting with acid form furfuryl derivatives by dehydration. Condensation with resorcinol produces this red color. Under acidic condition, keto group is more reactive than aldehyde group, and hence keto sugars readily give this test. Only ketohexose react much faster under this condition of the test. Boiling time is also critical. Prolonged boiling may give false positive for aldose, so you can't just keep boiling it, because again if glucose becomes positive, you will assume this is fructose, which is not needed. So you will have, don't prolong boil it. Next, coming to Osazone test, usually we don't perform this test, but you'll have to know it for viva point of view. In Osazone test, you take 5 ml of carbohydrate solution in a clean test tube, add 1 ml of acetate buffer and phenyl hydrochloride, and then after all of this, you just take that crystal, observe, and all of that. Glucosazone and fructosazone appears in 10 minutes in the water bath itself. As these ozones are insoluble in hot water, you need to know the shapes of it. Glucosazone and fructosazone form needle shaped crystals. Now you should also know the diagrams of it, just a needle shaped diagram, you can just put it. And then lactosazone and maltosazone crystals are formed after 30 minutes of boiling, so this take a lot of time. And ozones of reducing disaccharides are soluble in hot water but will crystallize on cooling. So lactosazone forms powder puff shaped crystal. Powder is white in color, lactose is kind of milk, so white, you just remember lactosazone forms powder puff shaped crystals. Maltosazone forms sunflower shaped crystals. You should know the diagram of it. Ozones of monosaccharides are insoluble in hot water and form crystals in the hot water bath itself. Ozones of reducing disaccharides are soluble in hot water, so they will form crystals only when the test tube cools. Okay. Principle of the test: reducing sugars answer this test. Presence of a free carbonyl group, aldehyde or ketone in the molecule is essential for this reaction. When reducing sugar is treated with phenyl hydrazine in acetic acid, first sugar phenyl hydrazones are obtained by the reaction of the reagent with the free carbonyl group. Product then reacts with more reagent to give sugar ozones, forming characteristic yellow or orange microscopic crystals. This is important, the color of the crystals, it is yellow or orange, which are useful in identification of different reducing sugars. Only the first two carbons are involved in ozone formation. Again, now this is a viva question. Since first two carbons are involved in ozone formation, the sugars that differ in configuration around the first two carbons, if the sugars are different only in the first two carbons, they give identical ozones, because this difference is masked by binding with phenyl hydrazine. That is why glucose, fructose, mannose produce similar types. They can ask why glucose, fructose, mannose give similar types needle shaped crystals, because they just differ in the first two carbons, and then this difference is marked by binding with phenyl hydrazine. Therefore, since these are the general reactions of carbohydrates, I'll just say all of those together. In my next video, you can see of each sugar, maybe glucose, fructose, and all of that. Let's just finish off with this last general reaction, that is acid hydrolysis, which you'll do it only for sucrose and starch. Okay, so you'll take 5 ml of carbohydrate solution and add 5 drops of concentrated hydrochloric acid, and then you'll boil it for 1 to 2 minutes. Then you'll cool it, neutralize it with 5 drops of 40% sodium hydroxide. Now after this, you will find this acid hydrolysis is complete. With this test, you will use the test hydrolysis test ka jo bhi sample is left, you will be using it for Benedict's test after hydrolysis. Again, you know Benedict's test, you will add 5 ml Benedict's reagent, 8 drops of neutralized hydrolysate, mix well, boil, brick red precipitate. The given solution on hydrolysis yields reducing sugars. Example, sucrose. Sucrose will not give Benedict's test normally. So after acid hydrolysis, you will do Benedict's test. Now since it has glucose and fructose, since these are reducing sugars, it will give positive Benedict's test. And next, Selvanov test, 2 ml of Selvanov reagent, 4 to 5 drops of neutralized hydrolysate. It will give cherry red color. Since after a breakdown of sucrose, it will have glucose, fructose. Fructose is a keto sugar. It will give cherry red color. Principle of the test: glycosidic linkage in sucrose, a non-reducing disaccharide, is easily hydrolyzed by dilute acid at elevated temperature. The product which is formed, that is glucose and fructose, will give Benedict's reagent, positive Selvanov reagent test, and then similarly polysaccharides are hydrolyzed by hot dilute mineral acid to yield monosaccharides which answer Benedict's. Basically, all this disaccharide ion, they are broken to its units, the monosaccharide units, which will give positive for Benedict's and Selvanov test. So we have done with the general reactions. In my next video we will see about each sugar. We'll just see all each sugar, what and all you can do, how it is gonna happen. Okay, bye guys, thank you, like, share, subscribe.